Good. So today's talk will be given by Dr. Shirley Ho, the leader of Cosmology and Data Science Group at the Flatiron Institute in New York, and a distinguished leader in bringing machine learning to astrophysics. Today, she will talk about how deep learning can help extract maximum information from the observations and about the vision for the field. So Shirley, please go ahead.
Hi, everyone. Let me just say hi to everybody and thank you for inviting me here. Can you guys hear okay or see the title screen okay? I think someone's speaking, but is muted.
Yeah, fine.
Okay, good. Can everyone sort of see everything more or less okay? And I would like to encourage people to basically sort of shout out questions. I won't be able to moderate while I'm giving the talk because it's the way the Zoom is. When you're sharing the slides, you don't get to see all the participants so easily. So people just should feel free to shout out questions anytime. I will try to pause, at certain parts when we finish certain sections about the talk for questions also, but just feel free to yell questions. I was one of those people who were trained by, I don't know if any one of you know Gerald Stryker very well, but he tends to ask questions very loudly, and I was a grad student in Princeton when he was very active. So we're very well trained to answer random questions at random points. And so just don't be shy, okay? And let me try to start. Okay, so today I'm going to talk about what can deep learning help in addressing astrophysical challenges. I'm Shirley Ho. I'm currently at Flatiron Institute as a group leader, and I also have joint appointments at Princeton, and also I'm an associate professor and with this adjunct position at Carnegie Mellon still, where I was tenured at Carnegie Mellon before I moved to Berkeley and then Flatiron. You might wonder why you move so much, but I guess just opportunities called when Flatiron Institute was first set up. Do anyone know about Flatiron Institute in this group? Yes, no? I can't see your heads for sure because I need to. A lot of people are not having videos up. No comments?
Don't be shy.
Don't be shy.
So you can also press space to unmute just momentarily.
Some of us are familiar with Flatiron, I think.
Okay, I'll just quickly say a few things. I've been in Flatiron Institute for about 2 years. And before that, it was basically an idea. It really was born out of an idea. A group of us went to Jim Simons and said, it would be really cool if we combine, these computational tools that people wanted or are developing and all the astrophysical and other challenges. Flatiron Institute has 4, actually now 5 different centers: computational astrophysics, computational biology, computational quantum systems, and computational for mathematics. And the newest one is for neuroscience. So a lot of these topics have challenges that could be possibly addressed by having more computational methods involved. And for CCA, the computational methods, not only just deep learning or other things like data science, but also simulations, numerical simulations, very heavy on that side too. And so that's why I was called and asked, what do you want to become a group leader to lead the group? You can name whatever group you want. Actually, it was kind of funny. And to look at how to apply the tools such as data science tools that we're developing very rapidly, such as deep learning, to astrophysics problems and challenges. So that's why I moved from sunny California to New York, which recently has become the headline in many different countries, I guess, because of COVID-19. All right, so that's the backstory. The work here I'm going to present are not possible without all these postdocs and students and my collaborators. I highlighted some of the postdocs here and the students here specifically because they did a lot of heavy lifting. CEO Hay, who's now moved to Plus AI, she was my Carnegie Mellon student, moved with me to Berkeley, then Flatiron, actually now graduated and happily working at the AI industry, making self-driving cars actually. Ying Li, who's at Flatiron, who's a postdoc at Flatiron. Paco, Francisco Navarro, Tristan Malfo, at Flatiron and Princeton, now just moved to Princeton recently. Gabriela Contardo at Flatiron, she's basically a complete machine learner, but recently has been, I guess, converted to astrophysics and machine learning. Jackie was an actually intern at summer from CUHK, which is Chinese University of Hong Kong. And he's moving to University of Wisconsin-Madison for grad school in the fall. Senior, and there's a bunch of NYU students here who did a lot of heavy lifting for one of the projects, are the master students for Center for Data Science. And Simon Ravanbakhsh and Barnabas Posso, Peter Battaglia, and Jeff Schneider are all machine learners from CMU, McGill, and DeepMind that we work heavily with. And yes, so this is not possible without the students. But without further ado, let me just talk about the work. So with this crew, I guess I don't have to explain why we care about the nature of dark matter or the nature of dark energy, that they might be the most two interesting open questions in physics. I mean, the xenon results you probably just heard recently got people very excited, and I would love to hear what people think about the xenon results that just came out afterwards. And then there's LHC, and of course in Europe there's huge amount of work in Euclid also. They are all costing possibly a lot. I mean, maybe you don't agree that the two most important or interesting questions in physics that are open, but arguably two of the most expensive one, I would say, the dark matter and the dark energy questions. So what do you take all this money, build these telescopes? What do you get? You get basically a observation of the universe. Here is actually a true real universe observed by Sloan Digital Sky Survey. And it was, every single dot here is a galaxy observed by Sloan. And you can see this large scale structure map in the video, and you say, okay, what does it do or tell us about the universe? And traditionally, that's what we do. We take this cosmic web, this distribution of matter in the universe, you plug it into some kind of pipeline, but really just summary statistics of the matter field or the galaxy field. We call it the correlation function on the right-hand side. And I'll click this and it will go. And as you can see that when you change the dark energy equation of state, which is basically a ratio between pressure and density of this unknown object or substance, whatever you want to call them, probably substance. And you'll see that the correlation function in the monopole on top and the quadruple in the bottom change. This is just observe summary statistics of the matter field. People tend to take the field on the left and compress it to the right. And then you'll compare it to the theoretical expectations, and you'll get a constraint on the dark energy here. You can probably see this is Planck 2018 paper, where if you take Planck, you get an TT, all the lensing stuff from CMB, you get this. This is the different parameterization of the dark energy. You can see WA, W naught for the experts here, but it's just one of the many parameterizations that people like to use to describe dark energy, sort of like a Taylor expansion. And then you can see that if you add BAO, which is basically from larger structure, and RSD and weak lensing, these are all from the cosmic web, which is the brown here. You can see this is shrunk dramatically. And if you add also supernova plus BAO, you shrink even more in terms of constraints on dark energy. Similar things happen when you look at other things such as the neutrino masses. Here we look at how you change sum of neutrino masses, and it changes the summary statistics also pretty dramatically when you hold all the other constants, basic cosmological parameters constants. And you can take a look of what it is computed here from this map to the summary statistics and compare to the theory, which is the predictions that we're just showing here with this marching sum of neutrino masses. And you can get a fairly good constraint on neutrino masses by combining CMB with larger structure, assuming different types of biases, either in 3D power spectrum or the 2D power spectrum, all combined. And how do you combine it with the cross correlations? And that gives you a better constraint on neutrino masses. So these things are what I usually do and I still do actually, sort of bread and butter how cosmological analysis are done. Is there any questions first? Let me just pause. Let me pause for questions. So I just ran through basically cosmology analysis 101. Yes.
So there's the constraint that I've heard on some of the neutrino masses is from cosmological data is 0.12 electron volts. Is that one of these combinations?
There is many different combinations, but yes, this is, I think 0.12 is pretty low. I think it depends on which basically confidence intervals you're quoting. So is it 2 sigma, 1 sigma, or like, is it just upper limit 95%? So yes, so when you say cosmology constraints on neutrinos, that's basically one of these combinations.
Okay, thanks.
Usually larger structure plus CMB. These are the two most, I guess people tend to trust it the most because they're all linear physics driven. When it's linear physics driven, you can just write down equations and you can predict what it should be without running any simulations. Any other questions? All right. I mean, I personally found Zoom talks very difficult because I cannot judge if people are just falling asleep or already brewing the coffee to survive the talk. But we'll try. Feel free to ask questions anytime. This is the easy part. So I was asking myself, can I do better than what we've done before, as all professors who got tenure tends to do? Like once you get tenure, decided you should do something different. Some people go off and want to become dean. Some people go off, do something else. I decided to try something sort of different from what I usually do. Because at that point, there's a lot of, I guess, hype in machine learning. And at some point, you ask yourself, if there's actual potential of really using it to transform in our field too. And it's also partially because I was in Carnegie Mellon, which is very, very strong machine learning. I think it's the only place in the country that has a machine learning department of its own, with their own hiring track, and a computer science school of over 300 faculties, like tenure track faculties. So everyone's talking about it. So I just decided to learn about it a little bit. And here's one of those things that you realize that they win against the best Go player in the world without, even playing against these people. They train the machine to play against itself, and it is discovered the 5 human Joseki, which are basically common corner sequences that are discovered during training. And he even beats the Go champion in the world over many, many games, not just one game. So that was pretty impressive when the machine can beat, a human who's really good at playing Go in that game. And of course, they've done a lot of other games since then. And then also something a bit more science-driven, right? Because deep learning also will apply to protein folding. They recently had, so for people who don't know about protein folding, it is very important because the ability to predict a protein shape is useful to the scientists because it's fundamental to understanding what it's doing in the body. And so diagnosing and treating diseases believed to be caused by misfolded proteins include like Alzheimer's, Parkinson's, or cystic fibrosis. So all these people, anyone can do it. People are given sequences of amino acids and they to predict the shape of the protein that were not published before at all. So out of 43 proteins, the second best competitor got 3 right, while the best team from Google DeepMind uses deep learning and got 25 out of 43 right. And here's an animation of what the gradient descent did, sort of unfolded and figure out how it's folded and predicted a structure for this target that no one has seen before. So I thought that was pretty cool. It even does something useful, not just playing games. And something more commonly used is how to detect objects and figuring out what that object is. And this is using residual neural net, which also won the competition in 2016. Things have changed a lot, but residual neural net is still used very heavily and in image recognition since it performs so well. And they won this common object in context competition where you can see from here that the person was recognized very easily, even a knife on the table or the wine glass is recognized and the cake too. So with a probability, which I think is quite interesting. So talking to people in CMU at that point, so Simon Ravanbakhsh started early with us. He was actually a postdoc at that point with us. Me and Jeff Schneider and Barnabas Possos, we looked at whether we can use machine learning as a very simple project. You throw these cubes of different cosmological constants. So these large number of cubes have different cosmological parameters. By eyes, you can barely tell the difference because if you look at them, they basically look the same. There's the big ones and small ones. The small one shows you basically what we feed into the machine learning code, because at that point, this is 2016, remind you guys, they weren't even 3D convolution. It was the first paper we wrote 3D convolution together to do this work. They were all still 2D, and there isn't enough memory basically to feed the whole volume in. You can only feed a tiny volume in. So we throw these things in and see whether we can extract more information from these data sets than what we traditionally do with, you remember all this correlation function we talked about earlier. So we throw this in. On the left-hand side is the input, on the right-hand side is the output. And you can see on the input, these little cubes is 64 cube. And you basically have a very simple neural net. I mean, now looking back in 2016, things have changed dramatically. This is probably one of the simplest network you will start with right now. You have few layers, and 6 convolution, 3 fully connected layers. The details are not important, but what's important is that on the left-hand side, you input cosmological cubes. On the right-hand side, outputs a cosmological parameter. So how does it do that? So you do it in 3 different steps. You have the input of the n-body simulations with known cosmological parameters. So you know what the cosmological parameters are. You have all the cubes. You train the network. When you train the network, you make the network learn all the different weights and constants, and biases. There's a bunch of names, but basically it's tuning a network, tweaking all the knobs until it gives you the best result for omega matter and sigma 8, that they will match for all the cubes that you input, that you know what the output is. And then you input the next set of simulation for validating, which basically usually means you want to fine tune all the hidden parameters of this neural net. And test set is what you do when you input n-body simulations with unknown cosmological parameters that you never seen before. Well, the network has never seen before, and see what the prediction went. This was published in International Conference in Machine Learning 2016, and it's a long time ago. Here is what we showed. It's sort of upshot plot. You see that the power spectrum analysis, which is what we usually do, has this huge spread. And it's not surprising for the cosmologists because we only put in a very tiny cube. It's not the full cosmological volume that you usually put in. It's such a tiny cube, you have a huge variance. While if you use the convolution neural net, you see this slightly biased, but definitely shrinkage of errors on omega matter. For sigma 8, it's not as obvious, but it's definitely lines better than the red line. And later on, we did actually redo this work and realizing that retraining the network slightly better and tuning the network slightly better, it will achieve even less bias from the convolution neural net. So upshot, it does achieve high accuracy than our traditional method. So I asked myself, whoa, okay, this is surprising. It was done in 2 months, and we just want to try if it's going to do something better than what we usually do with my bread and butter analysis tools that, sitting there. We've done it with Sloan, we've done it with Boss. So I figure, it cannot be so bad, but it's not doing as well as the neural net. So what are we missing here? Let me just pause if people have any questions. People, you need to yell because I need to be able to see you talking.
So how many different universes do you have to feed it to, so that when you train it, it can sort of tell you with another universe what the 3 interesting astrophysical parameters are?
Yeah, so we used about, I think 500 at that point. But honestly, we redid the whole analysis with slightly better tuned network. It's like 100. It also depends on the volume of the universe and how complex the universe simulation is. So when we use these simulations, they were not the most sophisticated n-body simulations. They were basically Kohler simulations for people who are experts in cosmological simulations. They are not full n-body simulations. They are basically fast approximate simulations. So they have less, how would I say? I would say there are less information in each of these boxes. While when we switched recently to redo this analysis just for fun, for training for the students, if you take the true n-body simulations, like Quixote simulations that Flatiron and Princeton has made it public We have petabytes of simulations with how many? Over 20,000 simulations, each 1 gigaparsec on the side. And it was like really good n-bar simulations. We only took 10. So that number is really not as important as basically how rich that data set is, I think, at some level. But that's a good question. Anyone else has another question?
Do you know what features I mean, you might be about to mention this. What sort of features, particularly in the omega M, what sort of features do you think that the convolutional neural net is managing to get that the regular sort of standard method isn't?
So we did not go too deep into it. As I mentioned, it was a work of 2 months, but we did look into this a little bit more in later different work. But for that paper, we looked at different feature maps. Mm-hmm. And I don't know if you can see my screen right now. I hope you can. That's the first layer convolution feature maps and the second layer convolution feature maps, like basically second convolution layer. And we pulled out the feature and try to look and see if there's anything obvious. Mm-hmm. So far, nothing too obvious yet, but you see structure basically. We had another work going on with the students where we take, that's not published yet, but we're writing it, where we take the cosmological simulation boxes, we put it into an autoencoder, which basically do multiple convolution, compressing the data, basically, and then try to look at in that bottleneck where things are compressed with least amount of bytes, basically contain that information, and then look at for each of them how it correlates with different cosmological parameters and what it looks like. If you take each vector, what it looks like, and it's interesting. It's not obvious what they are, but some of them do kind of look like, I don't know if people looked at wavelets, for example. It has some similar features of wavelets. It's not what you expect with clusters and filaments, but it's more like wavelet where you have, for different scales, they have different directions of filamentary structure. Okay. So that's what we saw so far, but there's a lot of work to be done there too, but that's another talk if you want to go there. Okay, but it's a really great question to look at the representation, what basically neural net is learning here.
And then you use the tuned network on the real universe to extract parameters?
Not yet, but that's the next part of the talk. And I'll explain why we need to do a bit more work to use the real universe here. Because if you notice, these are simulated universes, and they're only n-body simulations. They're not even true n-body simulations. They're fast, approximate n-body simulations of dark matter only. And our universe is way more complex than that. So you actually just preempted my introduction. What happened next is that, what are we missing here, right? We're inputting n-body simulations, basically of dark matter, to try to get the cosmological parameters. But what we really need is true, looking like a universe that we actually observed. But I can continue that part of the talk. Any other questions before I move on to the next part of the talk? Because that will answer the last question. All right. So as I was saying, now we're inputting these not fake, but basically simulated universes that are not very correctly representing our universe. So we want to actually input a true universe here and output the cosmological parameters, or you can make comparisons, which people tend to do directly from the observed data sets to something that truly look like our universe with all the imperfection and the perfection. So we want a universe that looks sort of like this, right? Because right now we only have, this is Sloan Digital Sky Survey, what they actually see when you look into the sky. Every single galaxy is real image of the universe. That's why it's blobby the further away you go. You're flying out from Earth, basically that's where the telescope look at, and you can see this larger structure. We want something this complex because you want to compare your data that you observe, say if it's Sloan telescope or Euclid or 2MASS, whatever you want to look at, or BOSS, and realizing that this is not so easy to simulate. So that's the next part of the talk. Interesting. Okay, so what do we want? What we want here is full-blown comparison between the observed universe versus the predicted universe. So the predicted universe here, even though I use Quixote simulations, which is mostly dark matter, it's just the dark matter simulations. But we want the full-blown one, which means includes hydrodynamics. You need to know what the galaxies look like so that you can actually use this to train the network, right? Like something that's looking like the real universe to train the network before you can input the true universe there. So generating one universe with all the necessary physics is expensive, and especially for large volume. For n-body dark matter only, it's not that expensive. It's completely doable, but it's still, when you want many, many of them, it could be expensive. But with, say, one single gravity only dark matter simulations of reasonable chunk of the universe, say a gigaparsec on the side, takes about 1.8 million CPU seconds. So I'm using seconds for a reason you'll see soon. And a small single volume gravity plus hydrodynamic simulations of the universe that includes baryons, dark matter, you know, gas particles, all that stuff. The universe takes about 1,800 or 1,800 million CPU seconds. Those are some serious numbers. And we need quite a lot of them to explore A, the cosmological parameter space, B, you want to estimate the accuracy of our constraints, and the parameter space in A that I mentioned here is not just cosmological parameters, but also various astrophysical parameters that connects from the dark matter evolution or basically underlying evolution to, you know, the galaxies itself, what the light will come out, you know, what kind of light will come out, what would you observe? So can we do that? So I claim that deep learning is coming to our rescue here, and we will try to do a full-blown comparison. And this comparison, you don't necessarily need to do with deep learning, which was what I suggested earlier, but you can also do it with traditional methods. People like to talk about like this likelihood-free inference. You can do however you want to compare, because the comparison is a different set of tools that you can do a neural net. You can do, you know, full-blown comparison with various different MCMC methods. You can also do reinforcement learning, recurrent inference machines. Like, there are many possibilities. So I'm not going to go to that, but today I'm going to talk about how do we use the universe to simulate the universe, how do you use machine learning to simulate the universe and do it fast. So that's what we're going to do today. So here is a simulation that we're actually using it as a training set. That's what we want to simulate very fast. It is currently at 3.2 billion years, and you probably will see some interesting explosion from supernova. And this is showing the temperature map of the universe. And you can see there's fairly complex things are happening everywhere. And it does affect how massive the galaxies are. You know, if there's stuff more blown out from the area, the more gas being blown out, maybe it changes the formation of the galaxies, and it changes the galaxy properties that we observe, and in turn tell you something different about the universe depending on how you model this and how you compare it with the observation. So it's pretty complex, and I thought it's really beautiful at the same time. It's hydrodynamics fully in there with gravity. And here I think it changes color is the metals. For the physicists here, the metals here is anything beyond like helium. So what we're going to do first, on the left-hand side, we have the dark matter simulations that looks way simpler. While the gas temperature, you can see all the explosion of supernova causing very huge variances in gas temperature. And he's just showing you the different redshifts as it goes down to 0.5, 0.49, it keeps going down. And you can see it's pretty complex, but all this time, the backbone of this structure on the gas temperature map sort of follows the dark matter map, which is very important. So the universe as we know it, we have the dark matter, we have the dark energy, we have the baryons, and all things interact through gravity, as I just shown earlier. It forms the backbone of the universe. So we want to model the gravity interactions first because it still takes 1.8 million CPU seconds to make one, with only the massive particles interacting gravitationally with dark energy included. So what did we do here? We want to use machine learning to simulate the universe, but only the gravity side first. And we'll go to the next part later. The input is an analytical approximation of the nonlinear evolution of the universe. The output is positions and velocities of all the particles evolved in the gravity after X years. And we have a machine learning model in the middle instead of the numerical simulations or Newton's law for all the particles with really good smart algorithms running really fast. And 1.8 million CPU seconds was not slow given the scale of things. We attempt to use machine learning to learn or interpolate from a large number of pre-run simulations. And people actually ask me how many number of simulations are actually needed. For the work that's published here, we use these fast PM simulations and we needed about 1,000. But recently we reran a bunch of this work with these complex simulations that are full n-body. We only took 10. And it did equally well. So we go from analytical approximation, something called established approximation field, to numerical simulated field on the right. So on the left-hand side is the input, on the right-hand side is the output. And something in the middle is this machine learning model that we used. This is work recently published, led by my students, who's now graduated, Shirley Ho, and it's published in Proceedings National Academy of Sciences in summer. And the network model is fairly simple. It's this residual neural net, but in U-shape. That's why people call it U-net. It has some interesting concatenation in the middle that is required because you want to have the large scale information coming into the output still, because the large scale analytical approximation is still correct. It's a small scale that's wrong. So you want the machine learning to learn what's needed, but also take from the input what is good. So that's sort of some design of the architecture and thought went into it. And then you see it dropping, going down. It's basically every single time you can kind of think of it, they're convolving with different scales and collapsing the information into the bottom. It's called the bottleneck, and you kind of expand it back up into the predictions. So what do we do? Actually, 8,000 pairs of simulations boxes. But again, we only need the 10 right now. We just realized when you use the complex simulations. We have 8,000 pairs of 3D boxes for training. And these pairs are analytical approximation on the top and numerical simulations in the bottom. You feed it to the neural nets, which is, it's called UNet. It's slight variance to residual neural net that people usually use to do image recognitions, whether it's a person that I talked about earlier. And then input and output looks really good soon. I'll show you why. So let me show you how well we do. We first will show the errors in displacement field predicted by our benchmark model, which is 2LPT, which runs really fast. It's second level perturbation theory. In our machine learning model, the displacement field is just the difference between the current position and initial positions of the particles. Here's how our benchmark performed. It performed fine. I mean, the error bar here shown is megaparsec over H, and the maximum error it ever got was 5 megaparsec over H, and most of the places 0 or to 0.7, and it actually strongly correlates with the overdense region. You see that when it's overdense, it's less well modeled, and I think we have some reasons to believe why that's the case. And for the machine learning model, you can see that the UNet displacement field, it looks really good. It basically has no red, and if you look at the numerical maximum for both, it's the UNet model performs 10 times better. Let's check a little bit more, and quantitatively, not just qualitatively. We check the following: the power spectrum of 1,000 simulations, the ratio. So these 1,000 simulations are predicted using the machine learning, and these 1,000 simulations predicted in 30 seconds. While I want to remind you that we can, for each training simulations, if you want the n-body ones, it's 1.8 million seconds. And we have checked and the ratio of the true power spectrum from either the machine learning or the benchmark, and the correlation coefficients. I'll show the equations next to the plot. I hope people can see. The large scale is to the left, the small scale is to the right, as usual. because it's easy to mix up sometimes. And you can see that, or you might not be able to see sometimes, the benchmark model is doing pretty well, actually. If you look at it, it's the blue line, and you can see it's following the prediction, the truth or the fast PM simulations pretty well. But if you look at the prediction with machine learning, on the top, you can barely see the orange line peaking from bottom below the green line. The green line is the truth. I don't know if you guys can see it properly. And Zoom right now refuses to let me find my arrow. Can you guys see it better this way? So basically the orange line is way hidden by the green line, which is the truth. And the orange is the prediction with the machine learning. If you look at the ratios, you can see the transfer function between the power spectrum from either the benchmark or the prediction to the truth here. Again, machine learning is doing really well compared to the benchmark model that also runs really fast. And also the correlation coefficient, which is important. The machine learning has much small error. This is 1 minus r squared, so lower is better. It's sort of equivalent to the area power spectrum here. And also, it is 16 million times faster. So that's good. So let me just pause it and see if there's any questions. Questions? No, everyone knows about my awesome work. No questions.
Real quick, what was the loss function for your unit?
The loss function is very simple. It's just the MSE between the displacement in the prediction and the truth.
Okay. Have we played around with that at all?
We did not at that point, but we did play with it afterwards. And then realizing that, at first I thought we should do some interesting physically driven constraints in the loss function or regularization for the machine learning crowd here. And realizing that, this MSE itself already contained the power spectrum sort of automatically, right? Because it's comparing whether the displacement field are doing really well, whether it should be where it's supposed to be. And so we could do a little bit more, but we haven't done a lot more in playing with the loss function. This is like off the box. We ran with UNet. We tuned the UNet parameters, but we didn't tinker with the loss function much. Any other questions? Yeah, good question.
Why did you choose the UNet over, for example, Hamiltonian flows or other generating flow networks?
Yeah, so it's funny. So at that point, UNet was not so popular yet. Remind you guys, this work started more or less 2016, 17. Actually, probably 16, 17. Yeah, 17, or maybe even a little bit talked about as 17. And I think UNet was doing really well in the medical imaging field, and we thought was quite interesting to try it out. We tried it out, it worked, and we didn't actually move to a different architecture. So it was sort of luck at the same time, but I believe there's some physical insights that drove us afterwards to think about, these are different scale convolution, and the fact there's concatenation, which means we can just take the info from the input directly to the output when the large scale is supposed to be correct. I think there's some analytical insight that we didn't expect to be that important, but it worked well. Other questions? If not, I'll keep going quickly so we don't stay too long because people will fall asleep. Oh, wow. I just realized if I do that, Zoom will actually just show me all your faces, which is great, but it will block my screen. And so we thought, okay, so there's just one more thing, right? We thought we can right now learn from a bunch of simulations. It can predict simulations of the same parameters, which is useful. You can make covariance matrices very fast, but it doesn't really do what I claim to do. What I claim to do is that we need to have different cosmological parameters for these simulations and do it really fast. Right now, what I just gave you earlier was basically predicting the same simulation, but 16 million times faster, which is cool, but not as cool as what we wanted. And so we tried to see something, whether it will happen, mostly because the student thought, why not we try? We input different analytical approximate maps of different cosmology, where the dark matter density parameter are different. So omega matter is like 0.1, 0.2, 0.4, 0.5, even try 0.9. Crazy ideas. And we did not retrain the network, which basically means the network has only seen omega matter equals 0.3. And see what happens. Can the learned model extrapolate a little bit and predict simulations that do not have the same cosmological parameters? The reason being, don't forget the analytical approximate still has all the large scale information correct, right? But all the small scale interactions, maybe it doesn't have as strong a dependence, maybe it does, of the cosmological parameters. So let's see what happens. So we did that. We check the following for different cosmological parameters for omega matter, for example. We still check the average power spectrum of 1,000 prediction seams, the ratios of true power spectrum, the area power spectrum, which is 1 minus r squared, r being the cross correlation coefficients. Here is a little bit more complex plot. The solid line is the simulation. The long dashed line is the prediction with machine learning. The short dashed line is the benchmark analytical approximation, which runs fast. So let's see what happened. I don't know if you guys can see, but let me get back out again so you can see a little better with hopefully some guidance on my mouse. The solid line is what we want because that's the truth. There are 3 different colors here for 3 different cosmological parameters, for same cosmological parameters for 3 different values. Omega matters to 0.1, 0.3, 0.5. Omega matters to 0.3 is what our training was at. So you expect it to do very well. And you can see that you basically do not see the long dashed line anywhere for orange because it's under the solid line. And surprisingly, it is nearly the same for omega matter equals 2.5 and 0.1. The long dashed line is well hidden under the solid line. Or you can look at the ratios here. And you can see basically the error is very small at about k equals to 0.7. And honestly, these plots has improved since because we trained it with a much more complex simulations. And it's in percent level without us retraining the network. So it is kind of interesting. We thought, what the heck happened? The model generalized significantly outside the training set. We did not explicitly use any transfer learning or meta-learning skills that people tend to do. You train something and you retrain it and do something different. Maybe there's an overlap of information somewhere between these universes, which is also possible. Maybe the universe is fairly simple, so the generalization extrapolation by the network is easy. Can we explain or interpret that? So I would usually go into interrogating this model with this afterwards, but I feel like with this crowd, I might just want to ask what people think happened. To give you a bit more hints, it also works with AS, not just omega matter. Let's see what people think. Suggestions, what happened? I can go back to the slide. It's not surprising, or I just put everyone to sleep. That also is possible. So we trained the network with one set of cosmology. Now we input different cosmology parameters, approximate maps. It still predicts basically the correct output. So it's kind of interesting, right? I'll leave this as a mystery for people in the interest of time because I want to tell you something further that I didn't usually talk about. So I'm going to skip forward to try to explain this a little bit more and show you the mini conclusion before I show you something else. Unless people really want to know what happened. I mean, we don't have the true answer yet also. This is just an investigation, what we have learned since. But I'm going to skip that part because seems like people can't come use over it. You can come back to me later on too. So the mini conclusion here, which I think is kind of cool to know. Sorry about that. Let me just make it better. Seems like the model is able to generalize way outside the training set. We have now cosmological simulations, particle interacting gravitationally that runs 30 million times faster than usual, or 60 million times. Doesn't matter. It depends a little bit on how much training do you use and which simulations you use as training set comparison. And for a variety of latent cosmological parameters, a little bit that you would know that the model actually has learned rotational symmetry, and the model agrees very well with perturbation theory. This is something we learned later. What should we do next, right? So we seem to have got the gravity simulations down, at least for omega matter and AS. We've actually been looking at sigma 8 and other parameters right now. So the next part is the harder part. The baryons describe everything we know, the protons, the electrons, neutrons, like all the elementary particles, but they interact not only through gravity, but also through hydrodynamics electromagnetically. So to model baryons is tricky. Remember the picture we showed earlier, these simulations, on the left is the dark matter, on the right is the gas temperature. The dark matter looks horribly simpler than the gas temperature if you look at this. But we wanted to simulate the baryons, which is on the right, much better and much faster. And the simulations on the right took 30 million CPU hours to generate. So 1,800 CPU seconds if I did it right. So when I try to do this machine learn the gravity plus hydrodynamic simulation of the universe, how do we do that? We want to go from, now we can generate gravity simulations super fast, like in milliseconds. Can I go from this gravity only simulations to gravity plus hydro to get the galaxy distribution correct? So that's the first step. It was published at NERSC, which is this machine learning, but one of the biggest machine learning conference. I think 14,000 people showed up when we went last year in December. So what we did is that on the left-hand side is this left column is a dark matter density field, just projected in 2D, so that not projected, just 2D slice. And on the right-hand side is this target distribution of galaxies. And you can see that you can barely see these little dots there. It's actually quite hard, and not that many galaxies are there, with so many more dark matter particles on the left. So it turns out to be not so simple. It's actually surprisingly harder project than the last one I described to you. But the idea is similar. You have maps on the left and you have maps on the right. The maps on the left is describing a field that you already have very easily accessible, you can create easily. The maps on the right takes 30 million CPU hours to create one little cube. So you want to sort of skip that procedure. And because it takes 30 million CPU hours to make this one simulation, we only got one as training set. No 10, no 1,000, just one. And here's the model structure we use. We use a two-phase model structure, which means that 2 steps. The first step basically figure out whether there is a galaxy or not. So it becomes a binary prediction. It's much easier to do. And then the second step is if there is a galaxy in that little pixel or voxel, how many are there? Which the second part is very similar to our UNet architecture, as you see in the bottom. It's nearly the same, but we decided to change a few things. There are reasons why we do it a certain ways, but we can talk about in details later. And now you can see our prediction on the right-hand side, and it looked pretty good. At least qualitatively, it looked basically the same as the target, which is in the middle. And you say, well, okay, it is a picture. So we can do a little better than just pictures. We calculated the power spectrum again of the predicted stimulation of the predicted galaxies. And we show you the ratios of the true power spectrum also. The whole process of training and prediction takes about 3 hours, and one training simulation takes 30 million CPU hours to do. So let's see whether this is actually any good. So the target is the green, which is what we want. The blue is our method. And the orange is the benchmark, is the halo occupation model that people always use. And honestly, one of my postdocs is the one who calculated, and he was like, I wish HOD was doing better. And you got to notice that the K for those cosmologists in place here, K value here is very high. It goes all the way to a few tens of K. And our model is correct to about K equal to 7. maybe 6, depending on how you read carefully on the transfer function, the ratios between the predicted power spectrum to the true power spectrum at the bottom. But you can see it's basically 1, which is the good number here you want, all the way to about 7 or 6, which is very small scale. And it's 30 million times faster. So we thought that was pretty cool. And now we are able to predict where and how many galaxies are there from a dark matter field. So now we have a fast simulation of dark matter, simulation with gravity. We actually don't need to run the hydro simulation anymore. You can actually get directly to the galaxies. What's after predicting the galaxies? Decided we want to predict some gas. It was another project because we know that we're going to observe a lot of interesting observations from 21 centimeter, all these, various different intensity mapping experiments, all this stuff that's coming up. There was this project was also conceived at Berkeley when Hera telescope is all in rage. For those who don't know about these 21 centimeter experiments. So our results of modeling gas in hydrodynamic simulation are accurate across 9 orders of magnitude compared to the simulations. We generate, if you want to generate a simulation, which I talk about, is this one simulation called Illustris, is 30 million CPU hours to generate it. The predictions took 2 seconds. And on one of these 2 rows, or 2 of these rows are the truth. The other 2 rows are the simulated universes. And I can try to make you tell me which one is the truth. Any suggestions? Let's see. Any takers?
The bottom is the truth.
Any other takers? To be honest, I actually don't remember. I need to go check my paper. For me, I can't tell the difference actually, because it's quite accurate, and you will see why I say that actually soon. Because qualitatively, you can't tell the difference, but qualitatively, we compare the Ford mass function. It matches really well. And the 1D PDF here, the blue line is what we want. The black line is the HOD model, which is sort of the benchmark model. Paco, which is one of the postdocs who was on this project, sort of pioneered right before this project. And it does really well for any heavy galaxies, but it did horribly with sort of low mass filamentary structures, laminar force. But our model is doing really well. Actually, the green line is the truth, the blue line is the truth, and the red line is our predictions. So it matches significantly better than the benchmark model. We also looked at the power spectrum. Again, the W again is the red line. It did pretty well with the error bars, and also compared to the benchmark, we're way closer. And so is the power spectrum. So is the bispectrum, where the bispectrum is basically 0 with HOD, while we can actually model the bispectrum quite well. The gist of it is the red and the blue dots are basically very close to each other. So what have we done so far? Go ahead.
Where did the error bars come from?
Yeah, this is a very, very good question. So the error bar came from the students running the many test cases and just looking at the variance of all test cases. And the test cases are very little cubes. Okay.
And how well calibrated are those?
Say that again.
How well calibrated are those error bars?
Not very well calibrated, because I don't think they did a very careful job in terms of including, possibly all the errors that you should be including. Like, I don't think they even calculate the cosmic variance, for example.
Okay, thank you.
Yeah, but this is, again, these are students who, this work is led by Center for Data Science master students. And there are 4 of them we supervised, and I was very impressed that we even get that far, honestly. Teaching master students in machine learning about bispectrum was interesting. So what have we done so far? We had approximate universe, analytical approximation of universe as input. You can get the full n-body simulations, and you can also go and get either the gas or the galaxy distribution. And you can see that the time it takes will be in the millions of CPU seconds or hours in this case. And now we have the situation where it's 0.03 seconds to get the full n-body simulations, which extrapolate well, surprisingly, and about 1 second to predict the galaxy positions, 2 seconds to predict the gas, the H1 in particular. So I would say, I guess I miss Obama, so I said, yes, we can. There's a full-blown comparison between the observed universe and the predicted universe. It seems like this is a way forward that you can predict. You can basically simulate fully the cosmological universe with both the gas and the galaxy density, number density, you know, with very, very little time. And you can compare it with the universe. There's, of course, a little bit more work, right? Because right now we have the number density of the galaxies, but we don't yet have colors or shapes. If you want to do weak lensing comparisons, we don't yet have the fluxes where you want to use emission line galaxies, but these are things we're moving forward. But I think the fact that it can even do what it has done so far and shown, I think it's very interesting. I'll give a quick conclusion because otherwise it will take forever. This process of inference that I just described is not specific to just cosmology, right? By comparing these predictive simulations and observed universe, in this case, but observable, is ubiquitous in everyday life, especially for scientists. So if deep learning can indeed approximate simulations and extrapolate outside the training set, it would dramatically expand the boundary of what scientists can do these days, and possibly other areas too. For example, self-driving cars. You know, if you can learn what happened when you can train with raining and sunny days, can you actually predict snowy days? I don't know. This might be very difficult, actually. Snowy because you obstruct the signs. Extrapolation or generalization outside training set is not guaranteed. We don't really know why generalization happens in some cases, or whether we can make this more robust, this transfer or generalization. Can we design architecture that allows this generalization to happen more naturally? There are probably other machine learning things we can do in terms of picking what simulations are more interesting to run, or what observations are most useful to make, like reinforcement learning would be one interesting idea to look into. There's a lot of hype and possibly a lot of potential in the crosstalk between machine learning and deep learning in sciences. So let's make it happen. And thank you.
So on this question of extrapolation, I mean, in particle physics, we always warn people against using a trained network on data which is outside the sort of the volume of the training data, because presumably the network can do anything it wants with data that sort of doesn't occur in the training set because it won't affect the cost. So it sort of sounds unusual that you can actually do it. So are there any hints about what it might be that's doing that for you?
We have a lot of, we actually have a bunch of projects sort of in that direction, trying to figure out why it's doing it for us, but we're not the only team that actually can extrapolate. There are a couple other teams that have this interesting situation where, let me bring out one interesting work by DeepMind. So Peter Battaglia and the group are able to simulate the universe, not the universe, particle simulations. And they were able to do extremely well in extrapolating and basically generalizing. Actually, I'm curious if I can show you guys the Twitter page. Actually, this will be way too much work, but they were able to generalize to different number of particles, different box sizes, even though they train with one single box sizes and one single total number of particles. And they were able to generalize going further in time steps also, while they train only with one time step. So there are generalization that's happening, but they have very strong, something called inductive bias. Like in the architecture, they made very strong assumption in the physical, by the physical biases. So I think there's some interesting ways that the machine learning world is discovering, is that if you put in interesting constraints from the physics world, you do much better in generalizations. So don't just take a network off the shelf and expect generalization. But I think there are situations where it does happen when you put in the right, they call it inductive bias, but basically strong constraint in the architecture based on your data. That's usually physical.
it seems you did not use a gauge equivalent neural network. So how did you train it to take into account rotational symmetry? Did you just augment your data set with all rotations, or?
Yeah, so our data sets were augmented. So we actually throw, you know, simulations that are, you know, this way, this way, this way, this way. So like throw it all, you know, all the rotations in, and it just learned it. It learned that it's rotationally invariant. But yeah, we did not put engagement variance in here. This is a good question. Any other questions? And I just realized we've actually have 1 hour mark. But we had a lot of questions in between, so I feel like it's better this way than me talking continuously for 40 minutes.
Sorry, I just have a follow-up question from the previous one about inductive biases. So with the simulations from Peter Battaglia, they used graph neural networks to sort of encode this, right?
Mm-hmm.
Is there anything that you had in your network that could be that you investigated and thought maybe this could be the thing that allowed generalization, or?
I don't think it was that obvious in our network actually. So this is actually a mystery so far still. I don't see any obvious reasons why it allows a generalization from our network. I pointed out Peter Battaglia's work because they seem to generalize fairly easily with the architecture, which is this graph neural net, which I suggested to talk about, but I think this one is easier for this audience. Our network is not specifically designed to have these strong constraints from cosmology in one way or the other. There's one thing we did that was different from that's a little bit unusual, is that we specifically wrote the periodic boundary conditions inside the network. So you tell the network that it is periodic boundary conditions outside the box. Okay. So, but that's it.
Okay.
Which is kind of cool.
How did you do that?
It's in the code. We can talk about it in details. Okay. But it's public. The whole code is public. Everything is public in this work. Actually, all our machine learning work were all public with the code and everything.
That's fantastic.